Okay, here we go, this chapter. Starting talking about exponential and logarithmic functions. And here's your topics for the chapter. We're discussing exponential basics and applications, logarithmic basics and applications, rules of logarithms, and then more complicated equations and applications involving logarithms and exponents. First off, what is an exponential function? Lots of things grow exponentially. A good example is bacteria. Talk about the way that bacteria grows. It splits and divides, right? You've got lots of things. I wish I knew more about science, but cell division, all these things, to where you have an exponential growth. And I'll show you what I mean by this. If something grows exponentially, splits into two, so what you started with one, all of a sudden now you have two. And then you've got that two that split, each of them split, and now you have four, right? And then when you take the 4 and all those splits, you have 8. You take those 8 and all those splits, you have 16, 32. And what you've got to be careful of, and I need to get Dale to come talk to y'all one day. I did a really good presentation when I was in school about this exact same thing, and I still remember it. But when something grows exponentially, an exponential growth is a fast growth. So think about it like this. If you started out with one bacteria, and let's say that this is a duplication, okay? Let's just say that each hour it doubles. And what I want to know is how many of that would you have after 24 hours? So what started as 1, after 1 hour is now 2, after another hour is now 4, is 6, 8, 16, and 32. That's only after 1, 2, 3, 4, 5 hours. What started as 1, you now have 32 of. After 6 hours, those 32 all split, you have 64. After another one, you have 128, 256, 512, 1,024, 2,048, 4,096, 8,192, 16,000, well, I don't really need to put a comma in there, 16,384, 32,768, and that was after 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 hours. So what started as 1, after 15 hours has already grown to 32,768. After 24 hours, let's use a calculator, my head's starting to hurt. We started at 1. And we're multiplying by 2. Well, after 1 hour, we multiplied by 2 once. After 2 hours, we multiplied by 2 twice. After 3 hours, multiplied by 2 3 times. So we're actually going to multiply that 1 times 2 24 times. And what started as 1, after 24 hours, has now grown to 16,777,216. So when something grows exponentially, okay, you see here a good example of how quickly it can grow. Another good example, there's an old story that, which it's fable, but this king offered, I believe it involved rice though, and I always use it as pennies, but it involved rice and gave this riddle about would you rather have this or would you rather have this, and my version of the story is asking the question, if you had the option between $1 million or I take a checkerboard and on the first square of the checkerboard I put a penny. On the second square of the checkerboard I put 2 pennies. And on each square I'm just going to double it. Okay, I'm going to put double the amount on the previous square on the next square. So on the third square I'll put 4 pennies. On the fifth square I'll put 8 pennies. Would you rather have $1 million or what's going to be on the last square of the checkerboard? And you probably already know, well, I'm going to take the checkerboard square because there's probably some sort of trick behind it, right? Let's figure out. And again, this is a good example of an exponential function. You started with a penny, and I'm going to double it. I'm going to multiply it by 2. Excuse me, each time I move to the next square of the checkerboard. Well, the first time, the first checkerboard square, I have 0.01 times 2 to the 0 power. I'm not going to double it yet. On the next square, I'm going to double it once. On the next square, I'm going to double it twice, and that's the third square. So once I get to the 64 square, see if it makes sense, then I'm actually going to double it 63 times. So that would actually be your exponential function. And that's what an exponential function looks like, is you've got some amount, and you're going to multiply it by some constant, such as 3, 4, 5, it could be anything. In this case, it's 2. You're going to multiply it by some constant x number of times, which in this case, actually x minus 1 number of times. This is the exponential function that represents this scenario. Is if on the 64 square, you want to know how much money you would actually have, that's how you'd figure it. So here we go. The amount of money on the last checkerboard square, some of you have already figured it out. You started with a penny, and you doubled it 63 times. So big you can't even fit on your calculator. That's called scientific notation. The E, that's how this calculator displays scientific notation. That means take 9.223372037 times 10 to the 16th power, move that decimal over 16 times. And that's the amount of money. Now that's the, that's money because I did 0.01. So I don't even know how big that number is. That's beyond millions and billions, right? That's huge. 92 quadrillion. I took that money. And that amazes me that something could grow that quickly. To go from a penny to 92 quadrillion or whatever this is in 64 terms. Which is very scary about, you talk about disease outbreak, all the Walking Dead fans and all that. You just see how quickly, when you're talking about bacteria growth, when you're talking about anything of that nature that grows that quickly. You know, if something, like we started that previous example, if something duplicates every hour or doubles every hour, and that would be easy to do, how quickly you could go from no big deal to mass hysteria. Okay, population growth is what actually we were talking about a while ago with Miss Robbins. Talking about population growth, population grows exponentially. Which also leads you to some fear that will we someday run out of room and won't have anywhere to put anybody on the earth? No, we'll never run out of room. We're going to run out of food first. So don't worry about the room. We'll always have plenty of room. The resources, that's what's going to kill us all. But anyway, exponential function, on a brighter note, an exponential function is a function of this form. It's, notice where your exponent is. 2 to the x power. Or excuse me, where your variable is, you have a variable in the exponent. And anytime that happens, you have really quick growth. Okay? So that's an example of an exponential function. Here, more exponential functions. Let f of x be 4 to the x power, g of x 5 to the 2 minus x, and h of x 1/3 to the x power. All three are examples of exponential functions. Some of them are actually exponential growth, to where things are getting bigger and bigger and bigger, and then you also have what's called exponential decay, where things are going away. Exponential decay, some examples of exponential decay would be like bone decay. If you've ever heard of carbon-13 or carbon-12 dating, excuse me, to where they try to estimate how old a dinosaur is by examining the amount of carbon in its bones. Carbon decays exponentially. And you can supposedly predict how old something is by seeing how much carbon is left in its bones. But anyway, back to this. This first part will just be reminders on, first off, function notation, and also your rules of exponents. So if f of x is 4 to the x power, there we go, got it back. If f of x is 4 to the x power, and you're asked to find f of 3/2. That would be 4 to the 3/2 power. Just a reminder, the bottom number is the radical, the top number is the exponent. So here you're taking the second root, the bottom number is the radical, the second root of 4 to the 3rd power. Also a reminder, you can do the root first or you can do the exponent first. It doesn't matter. In this case, and in all cases, I always do the root first. Just because then you're dealing with smaller numbers. If you do the exponent first, you're going to have to find 4 to the 3rd, which is 64, the square root of 64, which is 8, And we know that wasn't too bad, but I'd much rather do the square root of 4 is 2. 2 to the third power is 8. You can do it in either order. Next, we'll find g to the third power. If g of x is 5 to the 2 minus x, g of 3 is 5 to the 2 minus 3, or 5 to the negative 1. Also a reminder, when you're dealing with negative exponents, you need a fraction bar. Let's always leave our exponents as positive. Bring that 5 to the negative 1 to the bottom, and it becomes 5 to the positive 1. So g of 3 is 1/5. Okay, next problem. H of x is 1/3 to the x power. Again, exponential function because the variable's in the exponent. We're asked to find h of negative 2, which would be simply 1/3 to the negative 2 power. When a fraction is raised, and that's the reason I gave you these three problems, is just as a review. When a fraction is raised to a negative exponent, there's a shortcut. Take the whole fraction and flip it. I now have 3 over 1. And change the negative exponent to a positive exponent. In this case, you get 9. Okay, let's think about graphs of exponential functions. If you think real hard, you might have an idea what these graphs would look like. If I want to graph y equals 2 to the x power, well, first off, think about intercepts. What's my y-intercept going to be? Somebody tell me, please. How do you find a y-intercept? That's going to be a question every chapter. Say again. Plug 0 in for x. That's it. To find a y-intercept, plug in 0 for x. To find an x-intercept, plug in 0 for y. Let's find the two intercepts. Plug in 0 for x, you get y equals 1. Will y equals 1 always be the y-intercept of exponential functions? A lot of the times it will be, because 2 to the x, 3 to the x, 4 to the x, 5 to the x, it's always going to cross at 1. Why? Because anything to the 0 power is always 1. This is the only case to where it would not be. What if it was like 3 times 2 to the x? Then what's my y-intercept? 3, because that's 3 times 1. But most of the time, your y-intercept will be 1. X-intercept. To find an x-intercept, we have to find or plug in 0 for y. So you have 2 to the 0 power equals, or excuse me, 2 to the x power equals 0. So 2 to the x power equals 0. And now here's your common mistake. A lot of people say, oh yeah, 2 to some power is 0, that's 0. Think about what we just did. 2 to the 0 power is 1, not 0. 2 to some power is 0. What is that power? Let's try some. 2 to the first power, 2. 2 to the second power, 4. 2 to the third power, 8. 2 to the fourth power, 16. We've already done that once. That thing grows crazy. Okay, 2 to the fifth power, 6th power, 7th power, 2 to the 64th power, huge. So I think we need to go the other direction. Because 2 to any positive power is just getting bigger and bigger and bigger. Now 2 to 0 power is 1. 2 to the negative 1 power. 2 to the negative 1, you need a bar underneath, bring it to the bottom. 2 to the negative 1 is 1/2. 2 to the negative 2, again, put bar underneath, bring it to the bottom, that's 1/4. 2 to the negative 3 is 1/8. 2 to the negative 4 is 1/16. 2 to the negative 5 is 1/32. Do you see it's kind of the same thing in reverse? 2 to the negative 5 is 1/32. 2 to the negative 6 is 1/64. 1/128. 1/256. What is that approaching? Y'all remember that? 1/256, 512, 1024. Is that not approaching 1 over huge, which was 0? So as you're moving to the left, as you're plugging in negative values, you're getting close to 0. As you plug in positive values, you're getting close to huge. So here's what your graph looks like. And that should make sense why. So what x value can I plug in to give me a 0 for y? There's not one. Why? Because there's an asymptote line there. As you travel further and further to the left, you're getting closer and closer and closer to the x-axis, but you never approach it, or you never hit it. You approach it but never touch it. Because it's 1/256, 1/512, 1/1024, 1/2048, 1/10 trillion. That's still not 0. There's still a chance. All you lottery buffs out there, there's still a chance. 1/10,000 million trillion, there's still a chance. Okay? It's pretty much 0, but it's not 0. Okay? So that's the reason as you travel to the left, you're getting close to 0. As you travel to the right, you're getting close to huge. Okay? That's exponential growth. This also exponential growth. I'm just going to show you the graph. Same kind of thing. The only thing is it grows faster. This right here is kind of gives you your rate of growth. 2 to the x, that's pretty quick growth, but 10 to the x, start with 1. At hour 0, crosses at 1. At hour 1, you have 10. At hour 2, you already have 100. At hour 3, you already have 1,000, 10,000, 100,000, million. So that's really fast growth. Okay? So it shoots up faster. But again, notice it still crosses at 1 because 10 to the 0 is 1. Here you have an example of exponential decay. Because think about what happens with 1/2 to the x power. 1/2 to the 0 power, still 1. 1/2 to the first power is 1/2. 1/2 to the second power is 1/4. That's 1/2 times 1/2. 1/2 to the third power is 1/8. This is just like the 2 to the x power. It's kind of flip-flop, though, right? If you did 1/2 to the negative 1 power, think about how you do that. A fraction to a negative exponent, you flip the fraction and raise it to the positive exponent. So 1/2 to the negative 1 is 2. 1/2 to the negative 2 is 4. So it's identical to 2 to the x power, except for it's flipped left and right. Here is 2 to the x power, and here is 1/2 to the x power. It's exponential decay. It's like starting with 1 of something, and then it gets smaller and smaller and smaller and smaller as it approaches 0. Here's something else you can do with that. Let me just remind you about your rules of exponents. You can split that. So that's like 1 to the x power and 2 to the x power. 1 to any power is just 1. You can bring that to the top if you'd like. 1/2 to the x power is the same thing as 2 to the negative x power. Now let's go back and talk about transformation since everybody enjoyed it so much. If you take 2 to the x power and you turn it into 2 to the next negative x power, when you do pluses and minuses, you translate graphs. You move it left, right, up, and down. When you add and subtract, excuse me. If you multiply by numbers like 2 and 3, like if I did this whole thing times 3, you have stretches and compressions. When you have negatives, you have flips. When your x changes from positive x to a negative x, it flips horizontally. You see that's what happened there? That is simply a horizontal reflection because x changed to negative x. 3 to the negative x is going to be the same thing. 3 to the negative x is going to look like just like 3 to the positive x, which would look like this. Crosses at 0, 1. Then you have like 1, 3, 2, 9, 3, 27, 4, 81, and so on and so forth. It's the same thing flipped left to right, and here's a picture of that. Here's 3 to the negative x, which is exactly what we figured because here's 3 to the positive x. Okay, makes sense. And you still have the asymptote line, and you still have 0, 1 as your y-intercept. So that's enough about the graphs. Let's move on. Transformations. Let's go through and remind you, and I told you we do a lot of this year, and the reason I do so much of it is because I feel like it is vital to study graphs by looking at their transformations. But here's a reminder of everything, what we've actually done here, you have a new parent function. Your new parent function is an exponential function. 2 to the x power is exponential, that's a parent function. Now let's transform that parent function. Reminder, and let's remind you with something that we worked on before. If I turn x squared into x minus 3 squared, when you add a minus 3 plus 3 whatever, inside with the x, it translates it, is it up, down, or left and right? Anybody? Okay. Logan? Adding minuses or pluses inside with the x, up, down, or left and right? Think about x. With the x, left, right. It does backwards what you think it would do. If it's a minus 3, in this case, this would take this parabola and move it right 3. If we take pluses and minuses and we add it not inside with the x, but at the end, that moves it up, down. If you took, here's your next transformation, if you took the x and you multiplied it by something like 3. Things happen left and right there because it's applied directly to the x, but again, it's backwards. A multiplication of 3 would take this parabola, and it would actually compress it horizontally times a third. Now, if the 3 was being multiplied out front times the whole thing, not just the x, that would actually stretch it 3 times taller, because again, it's not applied to the x, it's applied to the whole function. And then your last two transformations, what if you took the x squared inside parentheses on just your x, you multiplied it by a negative, or you attached a negative to it? That's your flips. It would take that x squared and would actually flip it left to right. Because again, when things are applied directly to the x, they happen horizontally. So that would flip it across the y-axis, which in this case would do absolutely nothing. Because this would flip over here, this would flip over here. It'd be the same parabola. The reason why I squared them both, you still get positive x squared. And your last scenario is if you multiply the whole thing by negative, it would flip it vertically. That was your 6 transformations we discussed. Now let's do this one. Let's go from 2 to the x power to 2 to the x minus 3 power. Hopefully you got an idea of what that's going to look like. Here it is. 2 to the x power is your exponential function shown here. 2 to the x minus 3 power is that exact same function, simply shifted to the right 3 units. Okay, next problem. Describe each of the following graphs, or describe this graph. Your parent function. Here's how you find parent functions. Take away all the pluses and minuses, take away all the negatives. That's the parent function. Now that 3, again, that 3 simply tells you how quickly this thing's growing. Your parent functions on these could be 2 to the x power, 3 to the x power, 4 to the x power, 1/3 to the x power, 1/2 to the x power, but something to the x power is your parent function. In this case, 3 to the x. And we want to know how are we going to change going from 3 to the x power to this stuff, which is that. Now, my word of advice, the negative 4 out front, a lot of times people ask themselves, I really don't know what that negative 4 is going to do. Do this. Put it right there. That's 3 to the x plus 2 power minus 4. What I do like about these problems, it's easier to see is are the numbers being applied directly to the x, or are they applied to the whole function? If they're being applied directly to the x, obviously they'll be here. If it's applied to the whole function, it'll be either out front or over here. So the things that will happen horizontally will happen here. The things that happen vertically will either be out front, multiplied, or a negative, or being added, subtracted here. So there's two transformations here. Help me with them, Skylar. The plus 2 up here with the x will take your graph and do what with it? Moves it left 2 units. So you have your 3 to the x, which hopefully after those first few problems we know 3 to the x looks something like that, and it approaches 0 on the left. So there's your 3 to the x. So we're going to take that graph, we're going to move it left 2 units, and Henshaw, the minus 4 on the end does what to it? It's not multiplication, it's subtraction there. So this plus 2 moved it left 2, this minus 4 will move it not up but down. The only time you use backwards is when it's on the x. So there's your 2 graphs. Here's 3 to the x power, take this, move it left 2, move it down 4, and there's your new graph. Left 2, down 4. Any questions? Yeah, that's right. It threw me off when I saw the 1, but moving from 0, 1, what they did there, just to show you, they took that single point, they moved that point left 2 and down 4 units just to show you that point would still be on the function. Next problem, again, parent function here is the exact same. You have 3 to the x power, and we're going to transform that into negative, which is one transformation, 1/2, which is another transformation, times 3, that's from your parent function, to the negative x power. There's another transformation. 3 things are happening to this function. Just a reminder, HSRV is the order things happen. If you actually wanted to graph these, horizontal translations came first, stretches and compressions second, reflections third, and vertical translations come last. So let's go through and talk about the things that's happening here. Horizontal translations. Does the x have any pluses and minuses on it? What do you think, Carly? Any horizontal translations? Plus or minus anything? No. We're good there. Then we move on to stretches and compressions. Multiplying by a number will stretch and compress. We multiply by 1/2. Notice where the 1/2 is at. It's not up here in the x. Okay, it's out front. It's being applied to the whole graph. So we're going to stretch it vertically because it's not with the x, but it's applied to the whole. Vertically times 1/2. So we're actually compressing it half as tall. Reflections, there are two. You have a negative on the x, and you have a negative out front in front of the y, so it's going to reflect it across the x and y axis. The negative here flips it up and down. The negative here flips it left and right. So if you flip it left and right, that's across the y-axis. Flip it up and down, that's across the x-axis. So we're flipping it across both axes, and a vertical translation would be plus and minus out here or plus and minus in front. There are none. So those are all your transformations. Here's the graph of everything we just did. And they actually, you might be saying, well, I'm not seeing both the flips there. Look what they used as their parent function. I don't like that. They used 3 to the negative x, which here, let me draw 3 to the positive x. Here's the one I started with. Here's 3 to the positive x power. You took 3 to the positive x, you didn't move it, but you made it vertically half as tall. You see how this one's more short and stumpy. And then you flip it across both axes, so you flipped it here, and then you flipped it here. So you flip, and then first you compress vertically. Exponential equations, these are very ACT worthy. Okay, I could very well see some of these being on there. Just knowing how to manipulate these, and these are pretty basic that we're going to start with. 4 to some power is 1/4. From what we've already done, hopefully this is pretty easy now. You can plug and just try trial and error here. But guys, take this and write this as 4 to a power. 1/4 is the same thing. That's 4 to the first power. If you brought that back to the top, 1/4 is the same thing as 4 to the negative 1 power. So what is x? Negative 1. 4 to the negative 1 power, to make a negative exponent positive, you bring it to the bottom, and now it's positive. So 4 to the negative 1 power would be 1/4. 1/10 to the x power is 100. If we raise 1/10 to the positive 1, positive 2, positive 3, we're going to get smaller and smaller and smaller fractions. So first thing that's obvious to me is that x would have to be a negative number. When you make x a negative number, it takes this and it flips it over. So it's now 10 to what power? And we know 10 to the second power is 100, so that would be x must be negative 2. Again, the negative would flip your 1/10 over and give you positive 10, or excuse me, give you a whole 10, and then 10 to the second, that's where the 2 comes from, 10 to the second would be 100. So 1/10 for negative 2 flips it, raised to the second power, which gives you 100. 2 to the negative x is 1/8. You can think of this however you need to. If you need to go ahead and say, well, since it's a negative x, I'm going to bring it to the bottom, make it a positive x. And I asked myself, 2 to what power is 8? Finish that up for me, Kobe. Kobe here? No. Allie. 1/2 to the x equals 1/8. Really, the ones don't matter. 2 to what power is 8? Allie? 3. So x must be 3. 2 to the negative 3 power is the same thing as 1/2 to the positive 3, which would be 1/8. Let f of x be 5 to the 2 minus x power, such that f of x, and that's like saying y is this, and we want to make sure the y equals 125. So we're trying to find out the value that makes this equal to 125. Here's how I work it. I ask myself, 5 to what power gives me 125? 5 to the first, 5 to the second, I'll do that in my head. Brianna, do you know, 5 to what power is 125? Third. So therefore, does everybody understand that this has to equal 3? This has to be 5 to the third power, so why not just say 2 minus x equals 3? That's all you're solving there. And a 2 minus x equals 3, you're going to get x equals negative 1. You can move the x over here if you'd like, move the 3 if you want to do all that, but 2 minus what? Well, 2 minus 1 is 1. 2 minus minus, 2 minuses make a plus. 2 minus negative 1 is 3. Compounding interest, I think we'll have time to do this, and that's probably about it. Another application of exponential functions, and we're introducing all this stuff today. Then once we learn logarithms, which honestly logarithms is just another way of writing exponents, once we learn logarithms, we'll learn how to solve equations involving exponential functions. But the way banks compound interest, and let me explain this. When you invest money, when you put your money into a bank, let's say that you're putting $1,000 in there. You're going to put $1,000 in a savings account, and let's say that your bank, here's what it's called. Let's say that your bank compounds interest monthly. I need to explain first off what that means. Okay, let's say that you're earning like a 1% interest rate, or you're earning 1% in interest, and we're compounding interest monthly. Let's say, so after 1 month, 1%, you remember the old formula, interest equals principal times rate times time. It involves that, and it's similar to that, but banks really don't use that. So after 1 month, you've earned 1% in interest. What is 1% of 10,000? I think it's $10. Of 1,000, I think it's $10, right? So what that means, compounding interest monthly, it means after 1 month, they're going to calculate how much interest you've earned. And they're going to take not just the $1,000, but they're going to take that interest and put it with your other money that you have. So after 1 month, you no longer have $1,000. After 1 month, you have $1,010. Because interest is compounded monthly. After 2 months, now they take, and you're earning interest not just on the 1,000, but you're earning interest on the 1,010. So you don't earn $10 in interest anymore. You earn 10% of this, which is actually $10.10. So you now have $1,020.10. After another month, you're no longer earning interest on just 1,000. You're now earning interest on $1,020.10. So your interest is also gaining interest. And how often do they do that? I don't know. You'd have to ask them. Do they compound interest every month? Do they calculate? It's pretty much, when are they calculating your interest? How often would you like for them to calculate your interest? As often as possible. Because you want your interest to be gaining interest. Would you want it daily? Yeah. Would you want it by the minute? Yeah. What would be even better than that would be a continuous compounding of interest. And that's what we're going to talk about, is what would be the difference between, do they compound it every month, and do they take that money and put it back into your pile of money every month or every day, or so on and so forth. This is your formula, and you can add that formula to your formula sheet. The amount of interest, the amount of interest that your account will earn is based on P, the principal, that's how much you invest. The interest rate, which is R, and N is the number of times, that's the one people get mixed up on. N is the number of times your interest is compounded each year. Is it compounded monthly, daily? If it's monthly, that would be 12 a year. If it's daily, that would be 365 a year, that's if it's a leap year. If it were hourly, that would be a really big number. By the minute, even bigger. And then finally, in your formula, the T up here in the exponent is the amount of time that you're going to leave your money in the bank. So this tells you how much interest you've earned. So that's A equals principal times 1 plus rate over number of times raised to the number of times T power, N times T power. First problem. Find the value, or find the amount or future value when the principal of $20,000 is invested at 6% compounded daily for 3 years. You want to see how much your $20,000, and I think I lied to you. A is the amount that you have after. A is not the amount of interest that you've earned. A is the total amount of money that you now have. So again, here's your formula. A equals P times 1 plus R over N to the NT power. You have a principal of $20,000. That's how much you invest, $20,000. 1 plus your interest rate is 6%. Always make sure you turn that into a decimal. It's compounded daily. So Caleb Haynes, can you tell me what my N would be? 365 raised to the N times T power, so that's 365 times 3 years. So it's typing it into a calculator. That's all you're doing on these. Everybody got typed in yet? So we've got principal 20,000 times 1 plus, and here's where you got to be careful. I would go ahead and put that in parentheses. You don't have to, but I'm just OCD about stuff like that. 365, close parentheses again, raised to the, put parentheses around this as well, 365 times 3 power. Your $20,000 is now turned into $23,943.99. Okay, so you see that you've earned about $3,900 in interest. Or excuse me, yeah, $3,900. Now let's look at something. And I typed it in like this for this reason. What if we compounded it less often, more often? Let's see what kind of difference it would make. What if we compounded this thing instead of 365 times a year? Let's compound it, I don't know, 1,000 times a year, which would be more often, obviously, 3 times as often. Will it make a huge difference in the amount of money that we earn? Not a huge difference. You'll earn an extra $1. Why? Because daily is already, that's pretty often. Well, what if you compound it 1,000,000 times, 1,000,000,000,000 times? We'll get into that in just a second. Here it is. What you've got here is they took and they said, okay, let's say that we invest $10,000. And 1 plus interest rate here would be 12%. Man, that's a really good interest rate. I need to find that bank. Raised to the NT power, I think they're doing for 1 year. Yeah. And also, they're compounding it once. They're compounding it 4 times a year, which would be quarterly, is what that's called. Once would be annually. 4 times a year would be quarterly. 12 times a year would be monthly. 365 times a year, obviously, daily. There's 8,760 hours in a year, I assume. There's those scenarios. And look what's happening. Compounded annually. That's $11,200, and if I'm not mistaken, that would be your I equals P times R times T formula. If you'd like to try that, it's the same thing. That would tell you that you would earn $1,200 in interest over if your interest rate was 12%, and then add that back on, you get the same thing there. So that formula that you learned back in whatever grade, it only works for annually. But this other formula works for these others. But look what happens. 11,200, and it gets a little bit bigger each time you compound interest. Well, what's happening here? This value is getting bigger and bigger and bigger. That, again, what I'm discussing now is the foundations for everything you're doing in calculus. As that number gets bigger and bigger and bigger, this other number approaches something. It gets closer and closer and closer to some value. It kind of does that number, remember that leveling off? The amount of money that you're earning is pretty much leveling off. It's approaching some value. And that value that it's approaching is a continuous compounding of interest. That's like saying the millisecond that you compound your interest, you're going to turn right around and compound it again. So a continuous compounding of interest. How much time is between one compounding and the next? Pretty much nothing. It's like when we were talking about secant lines and that H value getting closer and closer and closer to 0. It's the same concept here. And all of a sudden, this number E pops up. I'm amazed by this number E. Have you ever heard of E? E is kind of like pi. You will be shocked. And this is, again, this is one of those things that just, to me, there's proof that something higher power is behind all this stuff that's generating this math. It amazes me because not only does this appear in this interest formula, but all of a sudden you see this number E appearing in lots of weird places, kind of like pi does. But if you have a continuous compounding of interest, all of a sudden your formula changes. And you don't have that A equals P times 1 plus R over n to the nt power. You have A equals PE to the RT power. APERT. This APERT formula is the exact same formula we're going to use for Newton's law of cooling. It's the exact same formula that you're going to use for radioactive dating. This formula appears a lot. So this number E appears in so many different applications. So there's your new pi number. So now we can have an E day in February. February the 7th is E day, I guess. Is that right? So 2.718. If the principal is compounded continuously. Let's work one problem, then I'm done. Find the amount of money when the principal $5,600 is invested at 6.25% interest rate, compounded continuously for 5 years and 9 months. That's just cruel. They give you a decimal for your interest rate, or a fraction for your interest rate, and a fraction for your years. It's not 5 years, it's not 6 years, it's somewhere between. So let's talk about how we're going to do that. APERT, anytime you have a continuous compounding of interest, A equals PE to the RT power, where P is the principal. We're investing $5,600. E is a number, 2.718, raised to the interest rate is 6.25%, which is 6.25%, then move your decimal. So we're going to raise that to the 0.0625 times T. 5 years, 9 months would be 5 9/12 of a year. It's not quite 6 years, it's a little over 5 years. 9 months is 9/12 of a year because there's 12 months in a year. So therefore, 5 9/12, if you reduce that down, is 5 3/4, which is 5.75. Type that straight into your calculator. So there it is, 5,600 times E to the whatever power, hit enter. Your 5,600 has now grown to $8,021.63. Last thing I want to say, there's actually, and this is odd, there's 2 E buttons on your calculator. This is the craziest thing. I think TI just needed something else to put over as another button. But you have an E button above the LN, that's E to the X. Then you have an E button above the division symbol. One of them is E to the X power. So it does that for you. The other one is just E. Well, they're interchangeable. If you want to put E to a power, you can use your caret, or if you want just plain old E, you can have done E to the first power. I don't know why they put 2 on there, but you can use either button. But that's what your money has grown into, is $8,021.